So let's attempt to do this reaction. So I've got an alkene, a cyclopentene group here, and I've got this real big scary system of reagents here. And again, if we don't memorize these things, we need to look them up. So specifically what we're looking for is this mercury acetate with, in this case here, it's an alcohol, and it's a two-step reaction that ends up using sodium borohydride to finish off the reaction. So let's go take a look at this. We're going to look either under reactions of alkenes or potentially synthesis of ethers, but under reactions of alkenes, I kind of gave away what we're going to get, didn't I? So under the reactions of alkenes, if we take a look, we've got different types of additions to, say, a double bond. I can add water across a double bond, create an alcohol. Here's mercury acetate, but it's using water and then sodium borohydride, so it's close. We're actually using an alcohol, so something very similar is going to happen. In this case here, an alcohols get created because of water, but what we're looking for is an alcohol, and here we go. So very specifically, this is what we're looking for. And we're using methanol. So here's the mercury acetate, we're using methanol. And what it's telling you is whatever is attached to the alcohol now forms an ether right here. And there's a very specific example. So on the double bond here, we're going to use the mercury acetate with the methanol and two-step sodium borohydride. And ultimately, we're going to create an ether in a Markovnikov orientation, which means it's the ether is going to go on the more substituted carbons. I had a choice here of the ether going here on this carbon or on this carbon. This is a 2' carbon. I've got 2 carbons attached to it. That's a 2'. And here I've got a primary carbon. I've only got 1 carbon attached to it. It's sitting at the end. So the Markovnikov addition will go to this second carbon right here. So we'll take a look at our situation. We have a double bond. We have a 2' carbon here. We have a 2' carbon here. So it doesn't actually matter in our case which side it gets attached to. So we're just going to attach it and see what happens. So we'll redraw the molecule. The double bond has now disappeared, and an alcohol is going to be put in its place in a Markovnikov orientation. So where you would really see this come through is if I were to, for example, have a double bond but now have a methyl group on it. I've got 2 choices of where the alcohol can get in this point. This is the most substituted. This is the 3'. This is a 2'. And so the Markovnikov addition would occur here. And so if I were to use this reagent to start with, I would end up with the alcohol in this position. This is the compound we're dealing with up top, but I just wanted to provide a secondary example for this. So to finish off, we have a cyclopentane group, and oh, I've made an error here. I put just a hydroxy group. I totally forgot. I have to put the methyl group on. There we go. Now I finished. And no one corrected me. Anyway, so we have a methoxy group, and it's in the 1 position of the cyclopentane. So I'm going to draw this as a 1-methoxy cyclopentane. It's not completely necessary to put the 1 out front since there's no other substituents on the ring, but I like to do it because it just reminds me that I should be numbering everything, and just in case there are other substituents, I don't want to forget to number everything that's on there. In this example, we have an alkene across a cyclopentene molecule. Note that there's a methyl group sticking out of this, and here is the reagent that we're adding to this. So let's go take a look at this because I'm pretty sure most of us don't have this memorized. Again, it's a reaction of an alkene. So on this page here, we'll see an alkene. There's our boron trihydride and THF. It goes through a 2-step reaction. So this attaches here. It tricks the compound into thinking that it should attack on the other side, and so the alcohol gets created in an anti-Markovnikov position. So here's the example here using a cyclohexene. You'll see the methyl group, and so the addition will occur across a double bond, but instead the alcohol is going to be on the anti-Markovnikov, not on the most substituted. This is the 3' carbon, that's a 2' carbon. The alcohol will get put onto the lower substituted, the 2' carbon rather than the 3' carbon. So let's apply that to what we have. So I'm going to redraw the cyclopentene, but I no longer have a double bond, and I know that anti-Markovnikov, if I have the two choices, there's a 3' carbon, 2' carbon. The alcohol is going to go anti-Markovnikov in this position. So in this case, we have a methyl group and a hydroxyl group associated on the cyclopentane group. The hydroxyl group is higher priority, so this is a cyclopentanol, and now it is the highest priority. I'm going to put a 1 here, and now in the 2 position is the methyl. So this is going to be a 2-methyl cyclopentanol. And again, my preference is to keep the numbers in. So 2-methyl cyclopentan-1-ol. Or you could have a 2-methyl 1-cyclopentanol. So my preference is this one. As if organic chemistry reactions couldn't get any more fun, we're going to do an oxidative cleavage here. And by that I mean we're going to break this one apart. So we're going to reuse reagents that are actually going to bust open this double bond. So let's take a look at some of those examples. So if I were to use this reagent here, ozone, and then a thiol afterwards, we're going to see what will happen to this. So again, using our trusty book, we're going to see we're in a section now called oxidative cleavage of alkenes. And so if I use ozone followed by the thiol, essentially, I'm going to break up this molecule. But the double bond, essentially, I'm going to break up this double bond, and whatever the carbons were attached here is still going to remain. So I'm still going to have everything attached. Note though that this gets oxidized, but it doesn't get fully oxidized to, say, a carboxylic acid in the case of using potassium permanganate. So what we need to be aware of is if we have primary carbons that are going to be cleaved out of this double bond, we're going to create an aldehyde, and if we have secondary carbons that are involved in the cleavage of the bond, that these are going to form ketones. So let's take a look at what we mean by that. So here I've got, on one side of the double bond, I've got a carbon, and if I were to kind of just do a dashed line through here, this carbon is attached to two different carbons, essentially, or 2 carbons associated with it. This is a secondary carbon. So the expectation is when this double bond breaks, there's going to be a ketone on this side. This carbon, when this double bond breaks, there's only one other carbon. This is a primary carbon when it's associated only with this other carbon behind it here. And so when it breaks, this is going to form an aldehyde. So let's take a look at what will happen. So I'm going to just finish there. This double bond is gone, and I still have this carbon here. So this is essentially the same thing. All I've done is removed this bond here, okay, the double bond. And so now what we're going to do is, in its place, we're going to put in the oxidized carbons. So I've got now an aldehyde in this place, and over here I'm going to have a ketone. So that's essentially what's happening. If I switch reagents, I can actually oxidize this further, but I'll show one more example where if we don't have that carbon, this methyl group here, and let's just say we repeat the same reagents again, so I've got ozone, and then I use the thiol like this. When this breaks apart, I'm going to redraw this molecule here. Those are the same 5 carbons, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, same carbons. The bond is gone in between, and so what I'm going to do is oxidize this, and since these are both primary carbons, I'm going to put an aldehyde at the end of each of these. Right, so you can see the difference then. So this gets oxidized as far as it can to the ketone. This can oxidize to the aldehyde if it was a primary. So this is since this is our compound of interest, though. We're going to count the carbons, so I'm going to go 1, use red, 1, 2, 3, 4, 5, 6. 6 carbons. Note that the aldehyde is higher in priority than the ketone, so this becomes the number 1 carbon, and I'm going to start from this side. So I've got a hexane, So I'll write hexane first. It's an aldehyde, so it's a hexanal, and in the 5 position is the ketone, and the ketone as a prefix is called a oxo. So in the 5 position is an oxo, and I'm going to say that it's a hex and 1 al. I could not put the 1 in here because I could assume that the aldehyde is in the 1 position and it's higher priority than the oxo. But again, I always like to put the numbers in here just because that's just me. I'm used to doing it. So this example is similar to the ozonolysis one. We're going to do an oxidative cleavage here, meaning we're going to break this double bond apart. The only difference is that this reagent is much harsher than the previous one. So we're going to find that these carbons are going to get oxidized as fully as they can. Since this is a secondary carbon, we're expecting that this is going to get oxidized to a ketone, and this one should be oxidized all the way through to a carboxylic acid. So let's take a look at what we can find. So under the reaction conditions here, we're using potassium permanganate. We're seeing that it's warm conditions, and we're breaking through the double bond. And so once the double bond disappears, this is where the double bond was. We're oxidizing each of these carbons. So this carbon gets oxidized, this one gets oxidized to as far as it can, essentially. So if I have a secondary carbon here, this is going to go to a ketone. If I have a primary carbon, as in this case here, this will go all the way through to a carboxylic acid, and that's what we're going to create. So let's redraw the molecule then, not including the double bond in between. And so again, this will get oxidized as fully as it can to the ketone, while this one will go all the way to the carboxylic acid overall. And so this is the highest priority carbon here with the carboxylic acid. So I'll start the numbering here: 1, 2, 3, 4, 5, 6. In the 5 position is an oxo. That's the ketone. It's lower priority, so it's called an oxo. And we have a hexanoic acid, so hexanoic, and then a space acid. So note that there's a space here like this. I don't need to put the 1 here. Normally for other compounds I'll put a 1, but the carboxylic acid is much higher priority than many functional groups, and it's sitting at the end. So I'm just going to call it the 5-oxohexanoic acid.